Hi, everybody. Thanks for joining me today for this AWS Online Tech Talk. My name is Willow Chandarina. I'm a product manager with the Amazon Elastic File System team. Today, I'm going to be talking about modernizing applications using containers, serverless, and Amazon Elastic File System. I'm going to start out by talking about app modernization, what it is, and how Amazon EFS can help with it. And then we're going to get into the technical bits of how to get started. First, how to set up EFS for your modern apps, and then how to connect to your EFS file system from the major app modernization services. First, Amazon Elastic Container Service, Amazon ECS, then Amazon Elastic Kubernetes Service, Amazon EKS, and then AWS Lambda. Once we walk through how to get started, we're going to talk about best practices for performance, cost, and how to ingest your data. So let's start out with a little primer on app modernization and where Amazon EFS fits in. First, let's just talk about why modernize. So many customers are modernizing their applications in order to seek three main benefits. The first one is a cost benefit. So by modernizing applications, customers are saving cost both by reducing their operations burden. In other words, they are removing the undifferentiated heavy lifting of managing their applications while they run and the underlying infrastructure. They're also saving cost by reducing the underutilization of the resources that they have deployed, whether it's compute resources that are underutilized or storage volumes. Next, customers are modernizing to increase their application agility, their ability to scale up and scale down their applications as the load on those applications goes up and down. Next, development teams that modernize their applications are able to get more agile themselves, because as part of modernizing, you modernize your development and deployment and operations processes. So these teams are able to develop and deploy applications quicker, have tighter turnaround times, and deliver more innovation, more features to their customers faster. Now, to modernize with AWS, customers are adopting one of our several compute services that enable the modernization of applications. And there is a continuum of how much control that you want to let AWS take on your behalf. So at the very bottom of the scale, we have Amazon EC2, in which case customers have full control over not only their applications, but also the infrastructure that those applications run in. On the other side of the spectrum, we have AWS Lambda, where the only thing that you as a customer need to manage is your own application code, and AWS Lambda manages all of the infrastructure, all of the data integrations, and all the operations around it. Not all companies are ready to give up control of every aspect of their application, so that there are other choices in between. Either you containerize your application and run it on instances you manage with Amazon ECS or EKS, or you leverage AWS Fargate, where you containerize your application, you launch it using ECS or EKS, but you leverage AWS Fargate to manage the actual running of your application, so you don't need to manage the compute instances that run underneath. So with each one of these, there's a different trade-off to make in how much control you have over the application, and also how much AWS takes on your behalf, and how much work we ultimately save you. So different development teams, different applications are appropriate for different aspects of this, but really anywhere you can get on this spectrum is a step in the direction of modernizing your application and seeking the benefits that I just mentioned. Now, the way this often looks when you modernize an existing application is you have a server today, and that server is either an on-premises server or an EC2 instance. and it's running some application, and that application is made up of code. Now you have two choices to modernize your application. One is you can containerize it and run that application using Amazon Elastic Container Service or Elastic Kubernetes Service with or without AWS Fargate. Or you can take the application code and deploy it to AWS Lambda and run it completely serverlessly. Like I mentioned earlier, the choice of whether to do one or the other is based on your preference and what kind of application you're trying to modernize. But one of these two is typically an option for any application out there. Now, many of the applications that customers are modernizing currently leverage external storage through the form of a network attached storage or storage area network, a SAN or a NAS. Now, when you modernize these applications and run them either as containers or Lambda functions, the need for external shared storage doesn't go away. So the big value of a file system like Amazon Elastic File System is it allows you to modernize the applications even that need persistent storage. So you can simply modernize your applications by containerizing or deploying them on Lambda and then having the modern container or function point at Amazon Elastic File System to serve that need. And the reason why your application may require persistent storage typically falls into one of two categories. First category is that your application needs to be long running and stateful, meaning that it needs the data that that application is working on to be persistent, even if the instance of that application crashes or gets rescheduled on a different piece of physical hardware. That's what we mean by persistent. Or if your application needs to share data between either different instances of itself or between different applications in an overall environment. So in summary, the two reasons you would want persistent storage either are to, for the persistent piece of it, having your data be resilient to anything that happens to the running instance of your application, or because you need to share it. Now, some examples of that, particularly in the container space where you could be modernizing an existing application that you're running, are developer tools. So tools like Jenkins, Jira, even Git have a need for persistence because you want to make sure that your CI/CD files or your bug reports or your source code are resilient to anything that happens in your compute infrastructure. To web and content management systems like WordPress, Drupal, Nginx, Apache, the list goes on that one. But in that case, it's both persistence because you want to make sure that your blogs and images and other web artifacts are persistent, but also for the sharing aspects of it, because as load goes up on your web property, you want to make sure that you can scale those out to meet that need. And you need the scale out instances of those web servers or content management systems to share the single source of truth persistent data, and that would sit in a shared file system. There's also several use cases within machine learning and data science that leverages persistent shared storage. One is in training machine learning models using MXNet or TensorFlow. So with those, you can speed up the training of a model by parallelizing it across multiple instances, all sharing a single view of data in the shared file system. There are also several tools that are used by data science teams, such as Jupyter, Jupyter Hub, Airflow, that leverage a persistent file store for any data that individual data scientists need to operate on for their notebooks or their ETL jobs. On the Lambda side, where a lot of the applications are newly developed or custom grown, there are a few additional use cases as well. So one is other machine learning and data science type workloads. So in Lambda, the property that a lot of customers are trying to use EFS to solve for is the fact that by default with Lambda functions, you have 512 megabytes of local storage to operate on. And in many cases, the ML inference file that you're trying to operate on or the ML libraries won't fit in that 512 megabytes of space. Now that Elastic File System is available for AWS Lambda, there are many use cases that you can now do because you have unlimited storage space now available for your Lambda function. So that means you can import large models, you can load whatever code libraries you want, and you can deploy modeling and AI solutions now with Lambda. Another example of what's now available with EFS and Lambda is the ability to do media processing within Lambda functions. Here, again, it's a matter of having unlimited space available for your Lambda functions. So now you can do image and video transcoding even at the greater than 512 megabyte space, but also now you can chop up those images into smaller bits and parallelize the process of modifying or transcoding those images across many Lambda functions that share a single file system. So there, the shared persistence layer comes in handy. Now, with all of these use cases and on modern app frameworks, what many customers have historically discovered is that traditional storage doesn't meet the needs of those modern applications. And that's because the traditional storage that customers might be used to on premises or even that they are managing themselves in AWS using EC2 instances has a lot of the same drawbacks that traditional compute does as well. So that's lack of scalability, that's application volumes filling up with application data and requiring manual intervention to either expand those volumes or in worst case, you need to buy more hardware to physically expand. The lack of agility that comes with developers always needing to talk to IT teams about their storage forecasts and any coordination around deploying storage volumes for new applications coming online limits the ability for developers to innovate. And then just the overall administration overhead of managing the hardware, the operating systems, the configurations, and everything that goes along with storage infrastructure. And it was those main challenges that led us to make available Amazon Elastic File System. So with Amazon Elastic File System, essentially what we've done is we've taken file storage, shared file storage, and made it serverless. And there are three primary capabilities of Elastic File Service. One is it is cloud native. Next, it's highly reliable, and it's cost optimized. So by cloud native, what we mean is we've built Amazon Elastic File System from the ground up to be a serverless cloud native file system, meaning customers don't have to manage any infrastructure, nor do you have to worry about any sort of capacity planning because it's 100% elastic. When you create a file system, you don't pay anything until you actually start ingesting your data. And you never have to tell us how much you plan to ingest because your storage volumes scale along with the data that you put in. It's also cloud native because it integrates with the key AWS services that you need to use to modernize your applications. So of course, EFS supports connections from Amazon EC2, but also from Amazon Elastic Container Service and Elastic Kubernetes Service with and without AWS Fargate and AWS Lambda, to name a few. Next, Amazon Elastic File System is highly reliable. Any data that you write to Amazon Elastic File System is written to at least 3 availability zones in the region that you're operating in, and that data is available from all availability zones within that region. It's because of that property that Elastic File System is considered a regional service. So a regional service is one where the resources that you manage operate on a whole region basis rather than on a particular availability zone. And it's that property that makes it really easy to work with your data using modern applications that are also taking advantage of regional services. Last, elastic file system is cost optimized. And it's cost optimized not only because of the elastic nature, where you never have to worry about underutilization of resources, but also because we have two storage classes that optimize your cost automatically. We have EFS standard, which is appropriate for the data that you're actively reading and writing because it has the best performance. And also EFS infrequent access, which saves you up to 92% on your cost by moving data that you aren't frequently reading or writing to a lower cost storage medium. And using Amazon Lifecycle Management, we automatically move data from EFS standard to EFS infrequent access to save you that cost without you manually intervening. So now when you add the benefits of Amazon Elastic File System to the benefits of the container services, AWS Fargate, AWS Lambda, you get several benefits that kind of magnify. So first, it's the simplicity of the whole thing. So using serverless compute like AWS Fargate and AWS Lambda with serverless storage, EFS, you can deploy applications that are 100% serverless, even though they're using several different services together. Next, we've done these integrations in such a way that puts the control in the developer's hands on how exactly the storage configuration is done. So you never, again, have to worry about coordinating between a storage team and a development team in figuring out how to allocate storage to applications. So this helps you move faster with your application deployments. Next, the availability and durability benefits stack with these services because they're consistent from service to service. So Amazon Elastic Container Service, Elastic Kubernetes Service, and EFS are all regional services, which means when you deploy an application using one of these services and that application uses EFS, you don't have to worry about which availability zone that application runs in. AWS Lambda also has this benefit. So really any of these modern compute services, whether it's containers or serverless, now make your application regional, where you don't have to worry about which availability zone you're running in. You're resilient to any sort of issues in one availability zone or another. Your application will move wherever there is the highest level of availability, and the storage works the same way, so you never have to think about that in your application. Next, all of these services have elastic in the name, and thus they're all elastic. And that not only means that your applications can scale their compute and storage together, which they can, but also that they can separately scale their compute and storage. So for example, if the application all of a sudden has many more requests coming in and needs to scale out the compute, it can do so without necessarily scaling out the storage. Likewise, if your application is not expected to need any compute resources in, say, an overnight period, you can scale that compute instance down to 0 and have all of the data persisted in Amazon Elastic File System, making it available for the next morning, that application to come up and pick up right where it left off. And last, we've integrated these in such a way that the security just makes sense. So I'll get into how this works in a little bit, but we, through identity and access management and EFS access points, have made it really easy to think about security with containers and your file system. So I want to walk through a few use cases in case studies of how customers are getting these advantages today. The first one is a company called Asurion, which is a company that sells extended support contracts on electronics. As you can imagine, a company like this does a lot of customer service work, and customer experience during those interactions is paramount to the overall success of the company. Their use case was to use machine learning to evaluate customer experience during customer service calls. So take the audio files from those calls, run them through different machine learning models in order to determine whether the customer had an overall good experience or not, so they could quickly take action to improve it. So what they wanted to do was run these machine learning inferences in real time so that they knew instantly what a customer's experience was for a particular call. And they wanted to do that in such a way that didn't require them to upfront deploy a lot of compute infrastructure. They wanted compute infrastructure that scaled along with their actual call volumes, which, as you can imagine, go up and down during the day. So they wanted to use AWS Lambda to do that because Lambda has the ability of scaling linearly along with actual demand. So you aren't paying for compute infrastructure unless there's actively some work to do. Now, their challenge was these audio files from support calls can be quite long, depending on how long those support calls took. So they wanted to make sure that they were able to have unlimited storage available to their Lambda function so that they could process any support call no matter how long it was. So what they ended up doing was taking AWS Lambda and EFS together to implement their inference function in order to, their first use case was to achieve scoring on how enthusiastic their support reps were as a measure of overall customer experience. So as you can see from the quote, initially they didn't know if they were going to be able to use AWS Lambda, but when they saw that EFS was available, they were easily able to implement their application, and now they're in production doing this and getting these benefits. Next, I want to highlight a company named Acquia. Acquia is a web and application hosting company. So they have many customers that are trusting them to host their website, their content management systems, their application, their overall digital experience. And what Acquia was seeking to do was improve their ability to scale with customer demand and simplify their overall operations. So previously, Acquia was hosting their customers using EC2, Amazon EC2 instances and self-managed storage. Now, what their solution was to get those benefits was they modernized their application by containerizing it. So their application is Drupal based, which is a popular content management system. So they containerized their Drupal instances as well as all of their application functions around it. And they deployed it on Amazon Elastic Kubernetes service and used Amazon Elastic File System for the persistence of all of their customer websites. And in doing so, they were able to increase their compute and storage utilization because now they weren't statically allocating either compute instances or storage volume to their customers. And they were able to lower their administration and operational burden because now they were using AWS managed services for a big portion of their infrastructure. So they were able to get lower TCO while increasing their ability to scale individual customer instances according to load, which was a big thing that we're trying to get. Another example is T-Mobile, the mobile carrier in the US. What they were, their big challenge was they wanted to better scale their customer-facing applications according to load. So similar to Acquia, they containerized their applications. They used EFS for persistence, and they were able to reduce their cost of storage by 70% by getting by no longer having the overhead of management, by getting better utilization, and now they were able to scale their applications along with demand. And last example is Discover, who built a data science platform in Amazon Elastic Kubernetes service using EFS. So the big benefit here is their data scientists are more productive because they each have their own personalized data science environment. And they're able to share data easily because there's a shared file system underneath the whole thing. They call that environment the Air9 environment. So now let's get into how to get started setting up EFS for these applications and connecting those applications to EFS. So the big thing that you should understand when setting up EFS for modern apps is security and identity. Really, everything else is just single-click setup. So with security and identity, it all comes down to two goals that you have. One is file systems should only be mountable by the applications that need them. Two is that applications that mount a file system should only have access to the data that it needs. So in this case, you want to make sure that a file system that is shared between 5 apps can get accessed only by those 5 applications. That's number one. And number two is each of those applications should only see the data that it needs, not the data for the other applications. Let's look at how to achieve that. So first, what we've done on the Amazon Elastic File System side is we've implemented Identity and Access Management, IAM, to allow you to define policies of which applications can connect to which file systems with which permissions. So you see here in the example, there's a file system that's being connected to by a Amazon Elastic Container Service task, as well as a AWS Lambda function. The task has what's called a task role associated with it. The Lambda function has what's called an execution role associated with it. And those are the roles that are evaluated when the application connects to EFS to determine whether it is allowed to do so or not. And there's two ways that you can configure IAM policies to manage this access. First is you can attach an identity policy to the role itself that gives it a particular permission on a particular resource, like the file system that it's connecting to. The other way that you can do it is you can attach a policy to the file system, so that's called a resource policy, and you can define the policy in terms of which actions can be performed by which roles. So there it depends on how you want to define your policy. You can use both of these together if you have complex policies that you need to define. But this is all standard identity and access management policies, similar to what you'd be using for other services like Amazon S3. So this makes it really easy to use cloud native security to control access to data with your modern applications. Just a little bit more on how to use this. There's actually 3 permissions that you can use to define how much access an application has to their file system. First is if you use the client mount action, what you are giving your application is read-only access to the file system. So you can see that this top task called anonymous task can read to the file system, but it cannot write to the file system. In the middle, the task semi-trust is a task that we trust for most things, but we don't trust them to read and write as an administrator or as root. So here we've given that application the client mount and client write access or actions. And what that means is it can write using a user ID of 5,000 or really anything other than user ID of 0, which you see here is squashed to a well-known user ID of 65535. So essentially what we've done is prevented that task from doing any administrative or root operations on their file system. And last, for those applications that you have full trust over, or maybe there's an application that is using a file system all on its own, you can provide an additional permission called client root access, which allows it to read and write data using root. So what we've talked about so far is how to use IAM to control which applications mount which file system. So if you remember, that's goal number 1 from the intro. So now let's talk about goal number 2. How do we make sure that applications only have access to the data that they need within the file system that they're connecting to? And to understand that, first we have to understand how identity works with modern application frameworks. First, with containers. So what we see here is we have a file system set up. That file system has 3 directories. One is 2 of them are home directories, one owned by Bob, another owned by Sally. And the last one is a shared directory owned by a group called BI users. So essentially here we have data already in our file system with permissions set based on ownership. Now, when we connect to that file system from a container running in ECS or EKS or really any container framework, what happens is that application tries to read and write from the file system, and the identity of the user on the file system is picked up from the identity that was baked into the container image itself. So here, this container image was built where the application would run as user root, group root, or user ID 0. So at build time, that was decided, and now when you run that application, it tries to do those operations as that user. So the key thing to understand here is the POSIX identity, or the identity that the file system sees, comes from the container image and not anything about the task or pod runtime. So the implication here is if you do a Docker run and pull a public Docker image, you really don't have control over how that image was built, and you may not know what user ID and group ID it's going to run as, which may not be the best thing to run against a file system that already has data set up. Now with functions, with Lambda functions, it's a similar situation, except you actually don't know what user ID and group ID are going to come in, because that's something that AWS handles under the hood. So it's not going to be root because of the way that we set it up, but you don't know what it's going to be either. So you can't depend on it for the purposes of access enforcement. Fortunately, we have a solution to this, and that solution is EFS access points. So to understand these, let's first look at the definition of an EFS access point. So this access point has a name, it's associated with a file system ID, and it has two key things that you configure. One is POSIX user, the other one is root directory. POSIX user lets you configure three fields: user ID, group ID, and secondary group IDs. Now what these do is this overrides the identity that comes from the container or the application. So now you don't have to know or care what user ID and group ID was built into your container, or which identity that Lambda is using under the hood. Instead, you can be assured that all operations performed on your file system happens as the user ID and group ID that you configure here. Next, there's a root directory associated with it, which allows you to pick which directory your application sees as root. So it's not necessarily going to get dropped into root of your file system. Each application can have its own home directory, so it has its own limited view of the overall data. And EFS will pre-create that file system with whichever permissions that you choose. So in this case, what we're asking EFS to do is create the path apps/myapp with the same user ID and group ID that we've defined our POSIX user to be. So that means this directory is going to be created and our user is going to be able to access it, which is what we want. So we see that there's two key properties of this. One is it enforces file system identity, so you no longer have to care about the actual identity of the application. Root users aren't going to escalate their access, arbitrary users aren't locked out, and it pre-creates any directories and permissions so that you don't have to. So just to get a view of how these work, now I've connected to a EFS access point from my application. And now when that application tries to do an operation as really any user ID, could be 0, could be 10,000, the access point is now going to rewrite that to 123, and that's what I can use for any of my file system permissions and ownership. And I can link this to the IAM policy of my file system to ensure that a particular application can only use a particular access point so that it can't bypass this behavior. So just walking through some best practices here. So first, if you're using containers, if you're using serverless, my advice is to always use access points, even if you only have a single application connecting to a file system. It just means that you no longer have to think about what identity your containers are using. It makes it easy for you to run different containers later. You can change the identity of your application and not disrupt how that application sees its data because they're completely decoupled. So it just makes your life easier both today and down the line. Where available, use IAM authorization to control access to your file systems. It's much easier than what was previously the best option, which was using network level policies to control it. In modern apps, you don't always know which IP address your application is going to be coming from. So by using IAM, you can know ahead of time what your policy is going to be. And always enable encryption at rest and encryption in motion. Both of them are single click enables. In fact, they're on by default if you do an EFS quick create. So you can get these security best practices by default and without any performance penalty. So now that we've created a file system and created access points and put a IAM policy on it, let's talk about how to actually connect your application from one of these modern compute services, starting with Elastic Container Service. So we see here just a diagram of how this works. So you configure what's called the EFS volume configuration for your task, and that defines which file system it connects to and how, and then that task can go on to run either on EC2 or on Fargate, depending on whether you want to manage the infrastructure or run it serverlessly. Now, in the console, when you create your task, the first thing that you do is you click a link called Add Volume, and it takes you into a dialog that looks like this. So the first thing that you would do in this dialog is select EFS for volume type, and then complete the drop-down box for which file system would you like to connect to. Once you select your file system, you can select the access point you want your application to connect to, and whether or not you want to enable encryption in transit or IAM authorization for that file system access. So it's simple to configure your file system. The only thing left to do after that is configure your mount point. So now this is the linkage between the file system and where it gets exposed inside your application. So here you simply select the volume that you just configured. So I call that Fargate demo EFS. And by putting /data in the container path, what's going to happen is your application, anytime it reads and writes data from that /data path, it's going to take place on your EFS file system. And really, that's all you have to do to get started with ECS. If you're more of a JSON configuration person, then here's what that looks like there. So we see here that there's your volume configuration with all the same stuff that I configured. And then you just referenced that volume in your mount points, give it the container path, and you can use this definition from the API, from CloudFormation, whatever you're most comfortable with. Next, let's talk about EKS. So with EKS, there are a lot of concepts at play for managing any sort of storage for your application. So there's the container storage interface, which is the latest way of managing any sort of volume for your application. We have an Amazon Elastic File System CSI driver, which is what converts those generic CSI interfaces into something that happens on EFS. And then we have a few different concepts that users interact with: storage class, persistent volume claim. Rather than getting into the definitions here, let's just talk through the examples. Before we do, in some cases, you would install the EFS CSI driver. So if you're running EKS using a group of your own EC2 instances, there's just a single command that you use to load that driver. If you're using EKS on Fargate, the installation is taken care of for you. Nothing to do there. So now that we're ready to get going, there are a couple of tasks that whoever is acting as an admin on that cluster, anyone who's just setting up the cluster for developers to launch applications, need to perform. So the first is to create a storage class, and that's really just as simple as defining a storage class with a name and then saying it's going to be backed by the EFS CSI driver. Next is, for each volume that you want a developer to have access to, you create what's called a persistent volume. So this is the actual linkage between a Kubernetes object and a file system on the back end. So we see here that you create this persistent volume, you link it with a storage class, and then you put a couple of configurations in there. The main one is what's called this VolumeHandle, which is a reference to a file system. Now, if you've used the CSI driver before, you may have used this VolumeHandle in the past. Now, it's changed a little bit. So the syntax for it, as of the 1.0 version, which launched a couple of months ago, is you can now encode your file system ID, the subpath of that file system, and an access point ID all inside this, joined by colons. So in the case that most of you are going to want is this mount and access points case, where you're going to give the file system ID, colon, colon, and then the access point ID. So what you're going to do as an administrator is create several file systems, and in each of those file systems create several access points and link those with persistent volumes. And what you do in that case is you're building a pool of persistent volumes that can then be claimed by developers using a persistent volume claim. So a developer comes along, they create a persistent volume claim, just referencing the storage class name. And what that's going to do is go and find any available persistent volume from that storage class and assign it to this persistent volume claim and make it available for the application. And the way you link it with your application is you just reference the persistent volume name in the volumes portion of your pod spec or your service spec or however you're defining your application. And that's it. And last, with AWS Lambda, from the Lambda console, you simply add a file system, and then you can, similar to ECS, use your dropdown to select the file system, select the access point, and the path where it is mounted inside your Lambda function, so the path at which any reads and writes are going to take place on EFS. So the order of operation here is to create your file system and all that stuff. You need to make sure that your function is configured for VPC and that your function is in the same VPC as your file system, and then select add file system with these parameters, and then you're good to go on launching your application and using EFS. So let's wrap up here with some best practices for performance, cost, and how to ingest your data. So for performance, in case you haven't been keeping track of our recent What's New announcements, we've made several performance improvement announcements. The two biggest ones are a 400% increase in read IOPS that you can perform on a general purpose mode file system, and the other is we've increased the maximum throughput that a single application or a single client can drive by 100%. So we've doubled the per application per client throughput. So for best practices, my recommendation is always start with general purpose file systems. It offers the best performance characteristics for applications that are doing many metadata operations. There is another mode of file system called Max.io, but you typically only see better performance with Max.io when you have a highly distributed application that's operating on many different files and directories. If that doesn't sound like your application, you're probably going to see better performance with general purpose because it has a lower latency profile for metadata operations like open, lookup, read, write, things like that. Next, configure provision throughput in order to make sure that your file system provides enough throughput for your application to get started. What happens with EFS throughput is in bursting mode, the throughput of your file system is based on how much data that you're currently storing. So if you have a brand new file system with no data, you may not have the throughput that your application needs. You can override that simply by configuring provision throughput. And as you add data to your file system, if you're ever entitled to more throughput than you've provisioned, we will flip you out of provision throughput mode and give you the higher of the two. So you don't have to worry about having to switch it later. So simply configure a minimum provision throughput that you know your application needs, and then you might grow out of it later without having to realize it. Last is make sure that you're monitoring things like your throughput, IOPS, and burst credits. There's a link in the bottom of this slide to a GitHub page with a sample dashboard to get you started. Next, I often get the question of, for my particular application, should I use EFS or EBS, Elastic Block Store? The simple answer there is, first, determine whether your application needs shared storage or not. So if you need shared storage between your containers or functions, then definitely use Amazon Elastic File System because it's a shared file system. EBS is single attach. There are some applications out there that always need single attach and may benefit from EBS, such as databases, MySQL, and things like that. The other reason why you may want Elastic File System is the regional nature of it. You have an application that might pop up in multiple availability zones, or you want to take advantage of spot pricing in different availability zones. So by having EFS, you never have to worry about where your data is. If you need point-in-time consistent snapshots, meaning consistent between different files within your file system or your volume, Elastic Block Store might be more appropriate because it has support for point-in-time snapshots. If you have a job-based application, so you're running HPC simulations or something like that, where there's high scale out, need for lots of throughput, tens of gigabytes or hundreds of gigabytes per second, you may also want to look at Amazon FSx for Lustre, which is optimized for use cases like that. Next, I mentioned this earlier, EFS has a storage class called EFS Infrequent Access, which is 92% lower cost than EFS Standard. And to get started with this, you simply enable EFS Lifecycle Management, and you choose a lifecycle management time. So that time can be set anywhere from 7 days to 90 days. And what that time is doing is any files that have not been read or written within that time interval are going to be automatically moved to the infrequent access storage class. Now, your applications and users aren't going to notice any difference. There's still a single namespace, all the metadata is held together. So you're still able to fully access, read and write those file systems in the infrequent access class. You just drastically lower the cost of your file system. So definitely encourage you turning this feature on. Next, you never want to be in a position where an application does something it shouldn't, or you fat finger a RM command and accidentally delete data that your applications need. To have peace of mind on this one, we recommend configuring AWS Backup. It's a managed backup service in the AWS portfolio, and it's super easy to set up. You can either have it automatically set up on your file system, or you can use tags to have a backup policy automatically pick up any existing file systems and back them up. And you can either restore whole file systems or single files or directories, should the need arise. And last, for migrating existing applications and data from on-premises into Elastic File System, we have a managed service called AWS Data Sync. So you simply deploy an agent, a data sync agent on premises, it links up with the managed component in AWS, and you can define movement policies either to move all of the data in a one-time fashion or move it periodically if you want to still use your on-premises environment for some time. So that wraps up what I wanted to share with you today. There are several resources online to learn more about this, depending on which framework and service that you want to use, whether it's containers or serverless. I recommend checking out these blog posts here, the documentation. We also have several customers and partners that have published blogs recently. So with that, I thank you for joining today. I can take questions, and I thank you all for joining me.